Welcome everyone. Kevin Carpenter here, back again with another interview for doing instructor interviews. This time with ACCU. We got
Mhm.
Phil Nash with us.
Right.
Phil's going to be doing a class on coroutines, understanding C++ coroutines, and so welcome, Phil.
Thank you. Good to see you again.
Good to see you. So, Phil, if you don't know, is the creator of Catch 2, the leading C++ testing framework, and one of my personal favorites. And if you haven't taken his Catch 2 class, not being offered this time, but it's also a
Mhm.
very good one. Um, he's got a great background between finance, mobile, and security, experience with Sonar Source, JetBrains. Um, I'd say a wealth of practical knowledge, but just catch Phil in the hall. It's great conversations. C++ Standards Committee, C++ London. We're busy, aren't we?
Yeah, a little bit too busy.
So, but here we're talking about your coroutine class that you're offering at ACCU. And
Yes.
so I want to get into that. So one of the things about coroutines is their potential to really increase performance, especially with like asynchronous tasks and such, and complex control flow. Is that something that you've noticed? I mean, does that resonate with how you see coroutines?
It does, but that might need a little bit of unpacking. Obviously, if we're doing C++, very often the reason we're doing that is to get the most performance out of something. We're very performance sensitive. Some applications more than others. And when the committee were designing coroutines for inclusion in C++, that was right to the front of their minds. But as an inherent part of coroutines as a concept, that can be in tension with that because whereas we're used to making function calls where we just sort of load a new stack frame and uh, we're not going to heap memory, which has an additional cost, and we can be very sensitive to that. With coroutines, because you can suspend and resume a coroutine, it has to live somewhere else. It can't just live on the stack, at least not always. So by default, you've got a heap allocation involved. And this is one of the first things that performance sensitive people pick up, and it's, oh, I can't pay the cost of a heap allocation. So there are a couple of ways around that that maybe we'll talk a little bit about later. We definitely cover that in the class. So that aside, actually the performance implications do have a lot to rather they impact the way that you use C++ coroutines a lot. So one of the big complaints is that it's very complex to actually build a coroutine in C++, and that's because you're really dealing with the nuts and bolts of how these things fit together, all the different possibilities, so that you're not going to pay any additional costs beyond that initial heap allocation.
Gotcha. I was going to say, that point of coroutines being challenging. Um, as we go through conferences, you have the year of different types of talks, and it's like this
Yeah.
last year or two has been a lot of coroutine talks, and at least for me, it's taken digesting multiple, and I still feel that I'm just getting a basic understanding of coroutines. But I mean, your course is going to go beyond just the basics of coroutines, right? It'll really dig into the way they work under the hood.
Yeah, well, again, the coroutines that we have, you sort of have to dig under the hood just to get anywhere at all, and that's why they are so complex to get into, and why you have that experience a lot of people do with you go to see one, two, maybe even three coroutines talks, and you come out thinking, well, that all made sense as it went, but I still don't know how to use coroutines because you just got to have too many things in your head at once to for it to all make sense. So where I have a whole day to to teach coroutines, we take a slightly slower pace and to really build up from scratch a piece at a time in a way that you can um, put off the bits you don't need to understand just yet and sort of backfill as you go. And so, um, not even by the end, but like by the mid morning, you've got a pretty solid understanding of the entry point at least, which is actually half the battle.
So I was going to say, when I think of, because I did take your TDD class, several years ago now, but do you do the same thing with your coroutines where you're building out, I remember your classes being rather hands-on, and is it that same
Mhm.
way that you're building out a piece as you go, so you're getting that hands-on experience while you're doing it?
Absolutely, yeah, 100%. That's the thing with the coroutine. If you go to see a coroutines talk, you don't really have that interactivity. You're watching the theory and some examples, and it sounds great, but you don't really come away feeling you've learnt anything. You really have to do it yourself. So my material is all about. I've got about, I don't know, 12 different exercises. So we'll uh, we'll go for every possible aspect. Both me sort of leading, and then you actually go away and you do it yourself, and then we come back and review.
That so I for me that actually works the best. I love
Yeah.
working on the tasks, and then you have everyone around to help too. So with coroutines, what are generators, and how will they be explored compared to C++26's std generate?
Yeah, it's good to bring that up actually, because that is one library that we do have now in the standard as of C++23. So it didn't make it into C++20 along with the original coroutines. But generators are a very common use of coroutines, a very specific use case where you have one bit of code that sort of in a loop is
Hmm.
generating values, hence the name.
Yep.
And when I say loop, it doesn't have to be literal for loop. You can actually have, because you use co-yield for this, you can have that sort of manually unrolled, if you like. Every
Yeah.
time it yields a value, you've got another bit of code that's using the coroutine that gets um, yielded to with the value, and that could be in a loop as well. And that outer loop, one way to implement that the interface is to give it an iterator based interface, which is it's not rocket science, but it's a little bit tedious to do. So we did that all manually with C++20, and C++23 std generator just gives you that interface, and it is very generic. Most of the time, 99% of the time, you want a generator. Std generator will do the job. And now it looks like, I don't know, you could write a generator in Python and in C++, and they won't actually look that different, which
Oh
you
wow.
couldn't say before.
I was going to say, I think Jonathan Mueller's talk on functional programming, I saw him use that in a few slides, and I was like, oh, that definitely cleans things up.
Oh, yeah.
Yeah. So what are awaiters, and how will the workshop cover them and using them effectively?
Yeah, so waiters are actually the most general type of coroutine keyword. They can do everything that co-yield for generators can do, but also everything that co-return can do. So co-return you have at the end of a coroutine, much the same way you have the return keyword at the end of a normal function. It just has to
Okay.
have a different keyword so that it invokes the coroutine machinery. But you don't actually need either of those. You can do it all with co-await. Obviously, it's easier to use the more specialized keywords. The co-await will give you the ability to suspend and resume, and
Hmm.
then there's like the shortcuts and things. So if the thing you're suspending and then waiting for is already available, it doesn't actually return control anywhere. And again, performance focused. So you've got all these different ways of short circuiting the process to give you the absolute minimum overhead. But assuming it does suspend, returns control to the caller can get a value out of that. They don't have to, so you can send information back. But then when they resume, they can also send information the other way, and that could be the thing that you're actually waiting for. You don't always have to wait for a value, but you can do. So
Okay.
you've got sort of two-way communication between the coroutine and the ultimate caller, and so lots of different ways that you can make that tie up.
So that makes me, when I think of the way that you're explaining that working, that then wants to lead me into, coroutines on different threads. So
Hmm.
um, how does the work, how are you going to address that? Because when I'm thinking of it passing things back and forth, and I'm thinking a shared state, is how does that work within threads?
Well, before we actually answer that, since you brought up threads, it is one of the big misconceptions that I often hear people when I hear about coroutines, but they have this assumption that it's all to do with threads. It's all like a threading mechanism,
Okay.
and I think the confusion comes from the fact that you can use coroutines to do asynchrony, and the way we've been doing asynchrony before has often been to use threads, but
Right.
they are separate things. You can mix threads with coroutines, and in fact, doing so can give you some really nice, clean ways to sort of hide all of the threading machinery and the points you actually need to synchronize and that sort of thing into the the coroutine infrastructure code. So when you do implement your own awaiter, for example, that's where you might put a thread scheduler and handle, how you're going to pass things off. Do you have a thread pool that you want to restart things on, that sort of thing. So you can definitely do all of that. And while it doesn't, it's not a magic wand that makes all the problems go away, but it actually gives you a much more structured way of thinking about things to actually help to guide you to get it right, while keeping both the coroutine code and the calling code actually much simpler and almost thread agnostic, if you like, to some extent. That said, so that there's much more you can do with threading, and in C++26 we get stood execution, the so-called senders receivers
Yep.
model, and that's what we call structured concurrency, and that's been designed to work again cleanly with coroutines as one way you can interact with senders receivers. And I'm not an expert on that, so I won't say too much more about it. But if you do want to do a lot of threading with coroutines, you might want to look at the senders receivers model, because even if you don't have C++26, there's the libunifex library from Meta that can do it today, and that might be a better way of doing that safely.
So, okay, that's a lot there. And I am saying that because my mind got stuck on the fact, when we were talking about the threading aspect, I have to agree, because when I was first, when I first think of coroutines and having it resume, but honestly, a coroutine is still running on the same thread when you're pausing and resuming it, correct?
That's right. Unless you explicitly bring in other threads, no threads will be involved. Coroutines themselves are effectively thread agnostic.
That's and so now, having said that, it's like I totally understand where you're saying the amount of tools that can give you to have, so you can actually have the coroutine or a portion of it actually resume on a separate thread, or running the coroutine fully on its own
Yeah,
thread.
that's right. Yeah. And in fact, this is one of the things where you need that extra level of control. There's one of the functions you have to implement in what we call your promise type is final suspend, which says whether your coroutine should finish in a suspended state or not. And one of the things I say in the class is you should almost always suspend from final suspend, which gives you this nice catchy acronym. Not. But, so by default, just the muscle memory, final suspend, suspend always.
Yeah.
Because what you actually want when you threading aside, you start a coroutine, it runs to completion, and then you usually want to interact with that coroutine after it's completed, like get a final value out or even just clean it up, something like that. You want that control. But if it's already gone, you can't do that anymore. But the reason you have that function there is because if the coroutine is now running on its own thread, it's got to
Yeah.
clean itself up. So once it's done, it goes away. You're not actually controlling that from the outside. So both ways are supported, but it does mean that you've got to implement this final suspend function every time.
Okay. Yeah. Interesting. So, one other kind of maybe random, but await transform and coroutine traits.
Mm-hmm.
How will those be covered?
Yeah, so these are a couple of the ways, again, that you can customize how coroutines work. So the await transform is actually part of, there's it's a little bit confusing. We have something called awaiters and
Hmm.
then something called awaitables.
Okay.
And all awaiters are also awaitables. And if you think of it as an awaitable is something that you are able to await,
Right.
that
Yep.
helps. So an awaiter is something with a very specific interface. So like the promise type that I mentioned earlier, there's certain functions you have to implement. So there's 3 functions on an awaiter you have to implement that get called by the coroutine machinery. Whereas an awaitable can be any type. And then you use either the co_await operator to map it, or await transform, which is then a function on your own promise type. So you can make it specific to your coroutine type. You can say, if I'm awaiting, we use an example of stood chrono milliseconds.
Okay.
If you say co-await some number of milliseconds, well, then it will say, I can map that to this awaiter, and now we've got a coroutine that we can, or an awaiter we can interact with our coroutine on, and then actually sleep for some number of seconds and maybe resume on a different thread, and we'll do all of that. So that's one of these customization points. Coroutine traits is another customization point that you probably use less often.
Hmm.
Uh, actually allows you to map to a specific promise type that might be somewhere else. Again, if you want to have your return type from the coroutine be something that's not itself coroutine aware, then you can do that with coroutine traits. So we'll cover all of that as well. It's just one of these. There's a whole range of different customization points that you may or may not need.
Gotcha. So integrating into modern C++ techniques, RAII, custom allocators, optimizing coroutine usages. Is learning how to apply these features in a practical way something that you're interested in, I guess?
Well, yeah. It's interesting, you talk about modern C++ techniques, and then the first one you mentioned is RAII, which we've had since the
Yes,
early 90s, but
exactly.
it's still a really important technique. And one of the things, again, about coroutines is you have this coroutine handle, and you'd think, well, it's got to be, some sort of RAII managed type, so we don't have to
Hmm.
worry about cleaning it up. No, it's actually an opaque type that you can consider basically just a wrapper for a pointer, a raw
Yep.
pointer. So you have to manage the lifetime of the coroutine. Like I said, it finishes in a suspended state usually. You've got to then clean it up by
Right.
calling destroy on this handle. So you can wrap that yourself in RAI types to give you either scoped semantics,
Okay.
so it just clean itself up at the end of the scope, but it's non-movable and non-copyable, or move only semantics, which is sometimes useful. Um, I've not yet found a case where copyable semantics are useful, unless because you could actually build like shared semantics on top. But all of that's up to you. So you have to um, build your own semantics, if you like, and we will touch on following the rule of zero on that
Yeah.
towards the end as well. Whereas you mentioned custom allocators as well, and that's a big topic, and that comes back to the very first question about performance, and I mentioned about that heap allocation. So
Yeah.
the two ways we can avoid that. One is to actually provide your own custom allocators.
Yep.
And technically, coroutines don't have an allocator interface in the way that something like std_vector does, but it does give you overloadable new and delete operators. So you can
Okay.
actually build your own allocator support in that way, and potentially even have coroutines running purely within a stack frame, just using that support. But under certain circumstances, the compiler is allowed to elide the heap allocation anyway if it can prove to itself that the lifetime of the coroutine is fully enclosed within its scope. And it's called sometimes called the halo optimization. I think it's a heap allocation elision. Unfortunately, in practice, it's not very widely supported and could be a bit fragile. Like we'll show in the class that just adding some logging into the
Okay.
coroutine, which you need to do a lot, but will
Yeah.
often just completely disable the halo optimization, even when you think it's really clear that it should be. So
Hmm.
you can also use those same new and delete operators to detect when halo is working or not. So you can verify for yourself if you're going to rely on it.
Interesting. Yeah. So the idea of using custom allocators with the new and delete, I did the talk at Meeting C++ on custom allocators, and it
Hmm.
is. Um, I would love to take the class to see how that ends up working with coroutines, just because
Right.
the amount of control, which I never understood that I had before, has my mind currently diving down a rabbit hole. But for anyone watching this, if you want to take Phil's class with custom allocators, then you want to get over to the ACCU website and get signed up. But also hang on through the end of the video, because when it's all over, you will find a discount code for 10% off on the class. And so, Phil, looking forward to seeing you at ACCU, and I hope you have a
Yep.
great class.
Thank you. You too. We'll see you there. All of you.
Thanks, Phil.
Bye.